In this lesson, we will discuss distorted models. In previous videos, we covered the theory behind conducting modeling studies. We start by developing a set of n-k pi groups, where n is the number of variables relevant to the problem and k is the number of reference dimensions. Pi 2 through pi n-k are the independent pi groups, and pi 1 is the dependent pi group which contains the dependent variable we are interested in studying. The similarity requirements specify how to conduct the modeling study so that the results from the model can be used to predict the behavior of the prototype. If we are able to meet the similarity requirements, similitude is attained and we can use the prediction equation, which states that the pi 1 group of the prototype is equal to the pi 1 group of the model. But if even one of the similarity requirements are not met, the model is distorted and pi 1 of the prototype will not equal pi 1 of the model. However, it is possible that the prediction equation can still yield useful results despite this distortion. Many models are distorted for practical reasons. For example, let's say we're designing a spillway for a dam where a gate can be raised or lowered to control the flow of water. And the image on the left shows the cross-section of the spillway and gate we want to build. Now, prior to building the spillway prototype, we want to study the flow characteristics using a model to determine whether significant erosion will occur at the base. When conducting modeling studies of open channel flows, which are flows of liquid that have a free surface exposed to the atmosphere, like this spillway, the flow characteristics depend on the shape of the channel as well as the Froude number Fr and Reynolds number Re. In order for the modeling results to be useful, we should try to attain similitude between the model and prototype. We can first attain geometric similarity by building a scale model of the prototype. For example, we can build a model where all the lengths are reduced by a factor of 100 compared to the lengths of the prototype. We'll call this length scale lambda L, and it will have a value of 1 over 100. We probably would not be able to reduce the surface roughness by exactly a factor of 100, so the model will be distorted with respect to surface roughness. But fortunately, surface roughness should not impact the flow characteristics of this system greatly, which means the distortion of the surface roughness should not impact the usefulness of the model for predicting the behavior of the prototype. So now that we've achieved geometric similarity, we will need to run the model at the same Froude number and the same Reynolds number as the prototype in order to achieve similitude. The Froude number is defined as the flow speed v over the square root of the gravitational acceleration g times a characteristic length of the system L. We want to run the model at a Froude number that equals the Froude number of the prototype when it is operational. That is, Frm equals Frp. Plugging in the expression for the Froude number and eliminating g because the gravitational acceleration is the same in the model and prototype, we have that the flow speed ratio, Vm over Vp, is equal to the square root of the length ratio, which is lambda L. So setting the length scale lambda L determines the flow speed we will need to use in the model. For example, if the length scale is 1 over 100, and the flow speed of the prototype is 10 meters per second, we should run the model with a flow speed of 1 meter per second. And since the flow speed is related to the volumetric flow rate, this also allows us to know what volumetric flow rate we should send through the gate in the modeling study. The last similarity requirement we need to address in order to attain similitude is the Reynolds number of the model should equal the Reynolds number of the prototype. That is, Rem equals Rep. We plug in the expression for the Reynolds number, which is density ρ times speed v times characteristic length L divided by the absolute viscosity mu. Rearranging the equation, we have that the flow speed in the model over the flow speed in the prototype times the length scale ratio equals the fluid density in the prototype over the fluid density in the model times the fluid's absolute viscosity in the model over the fluid's absolute viscosity in the prototype. The length scale is lambda L, and we found from the Froude number similarity requirement that the speed ratio is the square root of lambda L. This means the length scale to the 1.5 power equals the density of the fluid in the prototype over the density of the fluid in the model, times the absolute viscosity of the fluid in the model over the absolute viscosity of the fluid in the prototype. So now that we've established this last similarity requirement, let's think about whether we can actually attain this requirement. The spillway prototype likely would be quite large, and the model would need to be much smaller in order for the model to be cost-effective. So a length scale of something like 1/100 might be reasonable. In that case, the left side of the equation becomes 0.001. If we assume the water flowing over the prototype spillway will be at 20 degrees Celsius, the fluid density in the prototype will be 998 kilograms per cubic meter, and the fluid's absolute viscosity in the prototype will be 10 to the minus 3 newton-seconds per meter squared. This means we will need to use a liquid in the modeling study with a density ρm and absolute viscosity μm, such that the right side of the equation will equal 0.001. Now, although in theory it might be possible to find such a liquid, models of large bodies of water, such as spillways, dams, rivers, harbors, and so on, require a lot of liquid, and water is the only practical choice because it's inexpensive and non-toxic. So the only reasonable liquid to use in the model is water. Now, we could alter the absolute viscosity and density of the water in the model a little bit by heating or cooling the water, but the density and viscosity won't change by the several orders of magnitude needed to meet the Reynolds number similarity requirement. That means we should expect the right side of the equation to be on the order of 1, and the model of the spillway will be distorted with respect to Reynolds number similarity. But this may be okay. If the Reynolds number is high enough in the model and prototype, the turbulence in the water in both systems could be similar, ultimately resulting in similar flow patterns. When creating models of large bodies of water, it is common for the model to be 2 or 3 orders of magnitude smaller than the prototype in order for the model to be a reasonable size and to be cost-effective. If the length scale λL is very small, this can force engineers to intentionally distort the model to prevent unintended consequences. For example, let's say we want to make a model of a river to study the risk of flooding. A cross-section of the actual river and the model river are shown. It was decided that a length scale of 1/1000 will be used for the model. At some point along the river, the width across the river is 500 meters and the depth is 3 meters. A length scale of 1/1000 means the width of the river in the model will be 0.5 meters and the depth of the river in the model will be only 3 millimeters. And unfortunately, when the thickness of water is only a few millimeters, surface tension can impact the flow pattern significantly. But in the real river that's 3 meters deep, surface tension plays a negligible role in the flow patterns. We can get around this problem by intentionally distorting the depth of the river in the model. For example, we could make the depth in the model 30 millimeters instead of 3 millimeters, which means the length scale in the vertical direction would be 1/100 instead of 1/1000. This distortion makes the water deep enough to reduce the impact of surface tension on the flow patterns. When models are intentionally distorted in this manner, engineers may have to make additional modifications to the model in order for the model to produce useful results. Unfortunately, there are no general rules for dealing with distorted models. Engineers must use their experience and judgment when deciding if a distortion will impact the usefulness of the modeling results.